CERN is as you know, is the largest laboratory for particle physics in the world. It's an intergovernmental organization based in Geneva, although our facility extends across two countries, Switzerland and France. Our primary mission is fundamental research in particle physics, and particle physics is the most fundamental of all sciences, because it studies the smallest constituents of matter and of the universe, and so the basics of nature, if you want. And these studies have been awarded and rewarded during the decades with big discoveries. The Higgs boson is the last one in 2012, but other particles before, and also Nobel Prize given to scientists of the lab. The second important component of CERN is the fact that CERN is a driver of innovation and technology, because our scientific goals are extremely ambitious, and therefore to accomplish them, to achieve them, we need to develop new technologies in many fields. And what we do at CERN really requires new technologies in the field of particle accelerators, particle detectors, and big computing infrastructure. In general, fundamental research is a driver of innovation, and fundamental research is becoming more and more a driver of new technologies. Example of fields where CERN has been leading are the cryogenics, for instance, big data. Everybody knows that the World Wide Web was invented and developed at CERN. New materials, superconducting magnets, electronics, and so on and so forth. The third component, the third part of our mission is training of tomorrow's scientists, physicists, engineers, training of technicians, but also education of the general public. So we have many initiatives for high school kids and high school teachers, and we can discuss this later on perhaps. And last but not least, part of our missions, pretty much enshrined in CERN constitution, CERN convention that dates back to 1954. CERN is a concrete example of peaceful collaboration across the world. We have 18,000 scientists working at CERN, mainly physicists, more than 110 different nationalities. And some of them come from countries that are not really the best friends of each other, but at CERN they all work together, animated by the same passion for science. So this is CERN in just a few words. And I would like to stress that Austria, and we celebrate this year the 60th anniversary of Austria membership at CERN, has been a very, very strong partner over the years, contributing technologies, contributing brains, contributing young generation of bright scientists. And I think now my colleague Jochen Schick will tell a little bit more about Austria at CERN, but I will be also happy to complement it.
CERN is a user facility, so the primary aim of CERN is to provide an accelerator which cannot be operated, constructed by a single country to users. So we are users, so for example in Austria, and we are doing our research at CERN. So for us, CERN is essential, is crucial. We would not be able to do any particle physics here in Austria. We need CERN as an international lab to do our research. We have several participants in CERN here. We have roughly something the order of 110 users. We have also something like 90 people being employed at CERN, but 110 people users which are based here in Austria but do their research at CERN. And it's the Institute of High Energy Physics, where I come from, but also the Stefan Meyer Institute, but also the Technical University, the University of Vienna, but also the University of Innsbruck. They have all doing research at CERN, but not only particle physics. There are, for example, also experiments like the cloud experiment for climate studies are done at CERN, where the University of Vienna is involved, and Innsbruck. So for us, it's very important to go there to do our research.
The CERN budget is about 1.2 billion Swiss franc a year. I used to say, using more friendly units, that it corresponds on average to one cappuccino per European citizen per year. That's the order of magnitude of the budget. And Austria, so the member states contribute in proportion to their net national income. So Austria contribute about 2% of the budget, so 25 million Swiss francs a year. But CERN is so in terms of weight, for instance, for the decision, because CERN is governed by a body called the CERN Council, that is the decision-making body, and every country contribute with one vote. So by our convention, one country, one vote. So countries that contribute more or less, they all contribute with the same weight. So this is one important thing. Another important thing is to consider is that the return that a given country has in terms of industrial contracts, in terms of human resources. Austria is doing extremely well in terms of human resources return, in terms of people that, for instance, are hired at CERN, in terms of students, in terms of teachers, in terms of people, Austrian schools that benefit from experiences at CERN, visit at CERN, or activity CERN initiatives. Also on industrial return, you're doing quite well, not as well as some other few countries, but I will say quite at a very good level. You are also benefiting from technology transfer from CERN. So in Austria you have a center which is called MedAustron. Perhaps you know it, is in Niederösterreich. I think it's a center where patients affected by cancer are treated using a therapy which is based on proton beams. So you know the standard therapy is radiotherapy, where a patient is essentially bombarded by rays, by X-rays, which have the drawbacks that they expand everywhere at all places. So if you bombard someone with X-rays, they do not focus only on the tumor, but they spread over the surrounding healthy tissue. The proton therapy is a complementary therapy which has the advantage that protons lose all their energy at the target. So they are much more focused. They just destroy the tumor, the cancer, and so they are very good for patients affected by cancer, the cancer that is localized close to delicate organs, or also for kids, where you don't want, of course, to irradiate kids with massive dose of radiation. So this center is one of the pilot centers developed in Europe based on CERN technology. So it's an example of spin-off from CERN technologies, because the accelerator is based on technologies developed at CERN, which of course benefit a member state country.
One of the founders of the CMS experiment, one of the two multi-purpose experiments at the LHC, which was also where the Higgs was discovered in 2012, and we contributed to the construction, to the development, to the construction of the experiment, to the operation. And for example, there are much more particles produced than what we can record. So you have to make a selection immediately. What do you record? What do you throw away? And the first selection level was developed here in Austria, built here in Austria, and operated now at CERN. So I think it's fair to say that every Higgs which was discovered at the CMS had to go through the Austrian filter, and so if you throw away the wrong particle, you have a problem. So that was something we developed at our institute, and the research program of the CMS experiment with about 3,000 physicists is currently coordinated by a physicist from our institute. So that's also, so we play in some areas, we have really some key contribution, I could say.
I hope that Austria will continue to be a very strong partner, not only because Austria contributes to the budget of CERN, but also because, as we mentioned, Austria made very, very high quality contributions to CERN in terms of technologies, in terms of industry, in terms of human brains, and high-level scientists. So I hope that we'll continue to work together for many, many years to come. For Future Collider, after the LHC and its luminosity upgrade, which is now ongoing, there are two projects on the table that are being studied as design studies, but also at the level of R&D work for accelerator technology. One is a linear collider called CLIC, which would collide electron and positron beams. And the other one, the one that you mentioned, a circular collider, which would collide electron and positron, but also proton, like in the LHC and ion. Neither of them is approved. It's at the level of design studies, and at the moment, Europe, as perhaps you know, is updating. We are updating our strategy for particle physics. So every 6-7 years, the European community of high energy physics get together also with colleagues from other regions of the world, from the Americas and from Asia, and we develop the roadmap for the years to come. So we are in this phase now. We had a nice community meeting in Granada, in Spain, in May, where it's a bottom-up process where the community identifies the scientific priorities, and then the strategy will be drafted in January, and the Council, the CERN Council, is expected to approve it in May 2020. So we will see if the strategy will give an indication whether we should go with a linear collider or a circular collider. These are expensive projects, but it's not that this money has to be on the table today. This project will develop over decades, okay? We're talking about 70 years. So, and also, I think that as scientists, we should not give in on our, goals of pushing back the limit of knowledge. What we should do is also to work on the technologies that make these projects feasible and affordable technologically and financially. So we will work on developing the technologies that will allow us to build a future collider, whatever it will be. We don't know yet.
This design study was led by an Austrian, so who went to CERN as member of the Austrian doctoral program. So we have a very successful program that people can do their PhD at CERN on some technical work, get a degree at a university or some university here, technical university, for example. And that was somebody, Michael Benedikt, who was there and is now a member of the CERN staff, and he was leading this design study. So see, that's also impact from Austria at CERN.
We have an experiment at CERN which is called CLOUD. It's a chamber where you put some gas, and by using proton beams coming from one of our accelerators, you study the impact of cosmic rays on creation of, say, on cloud formation. Okay, to understand what is the natural genesis of clouds, to be confronted then with what we observe and the anthropogenic genesis. So we try to use now the beams that we have. Not many laboratories in Europe have proton beams, to see how the climate could change or could be affected by, for instance, cosmic rays or natural effects. So it gives input to all the discussion about climate change with some measure that can only be done in this context.